All right, let's take a look at what happens when we try and factor and we run out of possible rational zeros before we're fully factored. So that'll indicate that we have irrational or complex roots. And then how do we find those? How do we approach those? So we will look at, let's see here, 16x squared plus 44x minus 55. So we want to identify, we're going to start the same way, where we use the rational root theorem to identify the list of possible rational zeros, and then we're going to check those and see what happens. Now, something to be aware of is anytime you have an odd degree function, so just like the one that we have here, where it's got x cubed, okay, irrational and complex roots always come in pairs. So when you've got an x cubed like that, you know you're going to at least have one rational root. The other two may be irrational, they may be complex, or they may be rational as well. But there's going to be at least one rational root, so we should at least be able to factor out one linear term and get this down to a quadratic, and then check the other terms against it. So that'll be sort of the plan there, but it's something to be aware of. If it's even powers, then that's where we may not be able to factor at all. But that's not the sort of thing that you're probably likely to see a whole lot. So let's start with the rational root theorem. The constant term is 55, right? So constant is 55, and the factors of 55 are just 1 and 55, and then 5 and 11. And then our lead coefficient is just a 1 out front of that x. So that'll lead us to the only factors of 1 are 1 in itself, but we're just going to, you don't need to have multiple pairs. So 1 is plenty good. And then we're going to match up top at the bottom to come up with that list of possible rational roots. So we've got 1 over 1, which will be 1, 5 over 1, which will be 5, 11 over 1, which will be 11, and then 55 over 1, which will be 55. And remember, we care about both the positive and negative versions. We got to check all of those roots. So while it looks like 4 numbers, we got positive and negative. So it's a total of 8 things that we would potentially have to check at the maximum. Right? So we'll start the same way, where we take the polynomial and we just start doing synthetic division and checking to see what works. So these are all whole numbers, so there's no special place to start. So I would just start with positive 1, and we'll work our way down the list. Yesterday I mentioned, like, if we've got fractions or something like that, you might start by checking all the whole number roots before you start checking fractions, maybe to hopefully avoid using fractions if you can. So synthetic division, there are no missing terms, so that should be just fine. And we'll just start out with positive 1. So 1, 1, 17. And you can already sort of see that this one probably is not going to work out there. So that'll leave us with 51, 61, and then 55 plus negative 55 plus 61 will be 6. So that is not a root, right? So this one's not going to work. So we can cancel out 1, positive 1. We'll try negative 1 next. I'm just working my way down the list. 16, 44, negative 55. Negative 1, 15, 29. Oh, that was weird. And then negative 29. Obviously, negative 55 plus negative 29 is not going to be 0. We don't even need to necessarily calculate that. So negative 1's off the table. So positive and negative 1 don't work. So we'll move on to positive and negative 5. So positive 5. 1, 16, 44, negative 55. So again, you can sort of see this one ballooning, probably not going to work. So 149, obviously, big number, not going to be 0. So 5 is not going to work. All right, -5. Hopefully -5 will work. 1, 16, 44, 55. All right. -5 times 11 is going to be -55. We add those together, -11, and -5 times -11 will be 55, and -55 plus 55 will be 0. So -5 is going to be a factor. Okay. Blue. So that means that -5 corresponds to the factor x plus 5. Remember, we change what the sign looks like on the 0 when we write that into a factor, right? So I can rewrite out my original polynomial as f of x equals our new factor that we pulled out, plus whatever we have left over from the division, so remainder constant x squared, right? That's still our remaining polynomial that we have, x squared plus 11x minus 11. Now, if we were factoring, and I didn't know how this would turn out, right? We would just take this remaining polynomial and we would continue to check numbers from our rational roots list right here and see what works. However, x squared plus 11x minus 11 isn't going to factor, so we can try all of the rest of the numbers from the list and it's not going to work. When that happens, that means that the only way to break up this red polynomial is to break it up into either irrational roots or imaginary roots. So if we're talking specifically about factoring, we're not going to factor that anymore. We can't factor it anymore. So if you were just asked to factor, this is where you would stop, right? We're not going to, we don't want to break that up because we don't want to see factors that have imaginary numbers or square roots in them, right? However, if you were asked to find the zeros, then your first 0 is just the one that you found. So with the factor that worked, the first one's -5, and to find the other two, we would just have to use this polynomial, and we could quadratic formula, we could complete the square. Those are sort of the two options, given that I'm telling you that it's not going to factor. And if you want to prove that to yourself, you can go ahead and check the remaining numbers from this list to see if they work, but I'll guarantee you that you don't. So then we could use the quadratic formula and say, x equals -b square root of b squared minus 4ac over 2a, right? And so you simplify, and this one doesn't end up cleaning up very nice, but -11 plus or minus 121 plus 44 over 2, 65 over 2, right? And so in addition to the -5 that you have, you've got two other zeros here listed within that. So your zeros would be -5, -11, plus the square root of 165 over 2, and -11 minus the square root of 165 over 2. Those would be your other two zeros. But again, that does not pop up when we're factoring, so we want to leave it in this factored form with the quadratic. I know I said we're trying to get linear factors, but that's only the case if we're looking if we're ending up with rational zeros. And so in that case, we'll just leave it there. And if you're asked to find the zeros, then you would just use one of the solving quadratics that we talked about in the last unit.